In Houston, I'm John Herder. Tuesday, the 26th day of September. Great as always to have you along, everybody. From the Experts is a virtual networking opportunity flow accelerator, helping leaders across industries connect very quickly in a brief, moderated, interactive show format. Yeah, we're like a TED Talk with interaction. And if everything goes well, your curiosity spark, new ideas, accelerate action, and you may have helped yourself or somebody else solve that problem, make a connection, reaching the opportunity faster. Welcome to the fifth episode in our series of helping business leaders solving problems with AI in partnership with Hewlett Packard Enterprise. On the show today, power performance scaling data centers when the chips are down. Folks, help me welcome guest expert Ian Fender. Ian's principal product manager, accelerated computing at NVIDIA, including HPC AI compute products and the Grace CPU platform. Previously, Ian worked on hyperscale computing at a very large cloud service provider, where he directed the development of accelerated products, including large AI systems ranking in the top 10 of the top 500 supercomputer list. Ian holds a bachelor's degree in computer engineering, University of Washington, not too far from where he lives today. Ian, thank you very much for stopping in to shed some light and insight on how this data center powered paradigm shift is threatening businesses' ability to competitively scale and grow to meet their customer needs. So over to you.
Thanks so much, John. Good to be here this morning. I'd also like to introduce another colleague of mine who's going to kind of jump in. Ivan, do you want to go ahead and introduce yourself really quickly?
Sure. My name is Ivan Goldwasser. I do product marketing for the Grace and Grace Hopper products here, working closely with Ian. So glad to be here.
So one of the things that's sort of a core tenet of everything that we do here at NVIDIA and how we evaluate our products, the last 10 years, you might be used to people evaluating products on ultimate per socket performance, right? Really looking at the chip. What we try and do is look beyond the chip to an entire data center level. And I'll get into what that means in a second. But why we do that is because we fundamentally believe that there's a problem that people are going to encounter, which is that as we develop more and more accelerated compute capability and the appetite for AI-driven insights becomes greater and greater, as we have more IoT devices, more clients out there, more richness of data, higher data quality, we believe that the four walls of the data center will become a constricting element to growing features or to growing user base or to growing insights or quality of experience. And I think probably a lot of you have already seen this in some capacity or another. This is a simple flavor of the problem that, you have to buy more compute to expand your user base, or you have a new feature that you want to roll out. Have you ever had to taper the rollout of a new feature because you didn't have, capacity in your compute fleet to support it, right? These are the kinds of everyday scenarios people get into that I think are a little bit of a harbinger of what the future is going to be like. And the reason that the future is going to be like that is, first of all, gains in data center power efficiency have stalled during the past decade, right? We've flatlined on just the facilities efficiency. That's this chart on the left here, PUE, the proportion of energy that goes into a data center that actually goes to powering compute and IT equipment, as opposed to cooling and facilities and other stuff. And what you can see is that's actually made significant gains up until about the mid-2010s. And then it's tapered off because there's only so much you can do with air cooling, right? We're at the limits of physics. Likewise, right? We talked about AI driving the need for more compute. This is very, very clear when we look at the needs of compute to train generative AI models, right? Transformer models are now increasing almost order of magnitude year over year in the amount of flops you have to dump into training them. At the same time, data center energy usage is over 200 terawatt hours a year, and it's only growing, right? We're at 2% of global energy usage for our data centers today. In 2030, just a few years from now, we'll be at 5%. So we're going to literally more than double the amount of energy we're dumping into data centers. While that's happening, there's kind of three things to keep in mind. It's probably not surprising that data center spend is also roughly doubling, right? The amount of money people are spending on compute from 2023 to 2030. There's more data than ever. There's more insights to be gleaned using AI. And simply put, the requirements of building the kind of experiences people find rich are accelerating. The four walls of the data center don't scale this way. You still have to pour concrete. You still have to find electricity. And so generally what we see is the four walls of that data center, whether it's a 10 megawatt data center or 100 megawatt, one of 10 in the world hyperscale type data center, they're not getting faster overnight. Maybe your data center is just a couple racks in the back of a building. It doesn't matter. You're still limited by the space and availability you have. You can't scale that overnight. Now, generative AI, I talked about order of magnitude type increases in the capability of the models overnight and the types of compute needed to train them. We have a tool for generative AI, and that's called accelerators, right? That's called the GPU. And the GPU is still enjoying about 2x year over year performance gains because there's all these places we can go. We can go to sparsity. We can go to mixed precision modes. There's all these tools in the toolbox to make accelerated compute more efficient year over year, even though the silicon technology itself is what it is. The CPU, however, is a mature product, right? This is something that the industry has enjoyed for 30 plus years. And what's happening on the CPU side of things is that, as we know, Moore's law has sort of tapered off, and this whole era of free lunch is over. And what that means is for all the resources you dump into building a CPU being equal, the amount of silicon, the power, right? The generation of the chip that you're building, you're only getting about 5 to 10% year over year natural performance gains from the CPU if you don't change something like the amount of silicon area or the power. So that's very different than what we see on GPUs, which are still growing at this clip of 2x year over year. And what that means is the workloads that can't be accelerated are not moving anywhere on performance per watt. And performance per watt is what dictates how much compute you can fit in your data center. So what's happened here is CPU vendors have stacked more and more cores, and they've done this at the consequence of power efficiency. So it's great that we have these many core CPUs, but it also means that if that data center per watt metric dictates how much compute you can actually put in the DC, we're just sort of treading water. We're still at that sort of 5 to 10% a year natural performance gain clip that we get out of silicon in the post Moore's law type era. Because of this, there are a few different directions people are taking architecturally to try and get around this problem. But I want to pause here and sort of open it up to the group and get any thoughts that you guys have on, where you've seen capacity growth become an issue, or if you've noticed this sort of growing gap between CPU performance improvement and accelerated performance improvement.
Ian, this is Jason Bell from JLL. How are you?
Hey, doing well. How are you, Jason? Good morning.
Good. So just and it's great to connect with you guys. We're one of the leading kind of data center advisors for AI hyperscale and enterprise in terms of deployments. And you're exactly the challenge that we see right now. So in terms of space and power, today the CPU is in an air-cooled environment. Right now with the GPU and NVIDIA and H100, it appears that you can get 45 kW per rack in a standard air-cooled environment. But the roadmap for these providers is going to be greater than that. So the question, and we're still tracking this, is the kind of transition to liquid cooling, which is at the early stages in the market expensive, and then the stage to immersion cooling, which seems to be a 2025 market entry maturity. So what are you all seeing? I'd love to get your take on it because we're tracking this. We just have not seen enough of the liquid and immersion in the market today, and everybody is still leveraging traditional tier 3 data center co-location operators to support hyperscale LI and enterprise. So sorry for the long-winded question, but I think you're...
No, it's a very good question. And we're not going to talk too much about liquid cooling versus air in this talk, because fundamentally what we're focused on is the challenge that you need liquid cooling when the density, the power density of a chip, for instance, or a box in your rack becomes really high. But at the end of the day, we still think that you're limited by the amount of power going into the building at some point or another, right? So, you know, that 10 megawatt data center you have doesn't become 20 overnight, liquid or not. It helps bring your PUE down, you know, from 1.25 to 1.1, you know, so you get a little bit back. But, you know, in answer to kind of your point there, I think that we're going to see liquid cooling first on the types of systems that absolutely require it. And that's going to be high-end accelerated systems. So my goal for running our CPU product is to make sure that for the rest of the compute that supports that infrastructure, right, that's hosting your data, that's feeding the accelerators, I want people to have a long and happy tenure on air cooling. Because I agree with you that it's not going to be ubiquitous overnight, right? So if you have some appetite, you have some space, some capacity that you can actually, there's money to put into liquid cooling, I want you to put that on the types of chips that are at the absolute bleeding edge of accelerated compute and not on your CPU.
Right, thank you.
Yeah, no, great question. And that's exactly what you're seeing here, Jason, where the concern is like, look at like Milan, 280 watts up to 360 watts in 2022, right? Like what's next? There's going to be a point where these things have to be liquid cooled, certainly. And we also expect to see things, Jason, like air cooled servers. The most popular air cooled server today might be a two socket machine. Does that hold true in an era where CPU TDPs are higher? Right.
No, I totally agree.
So the way that the industry is trying to balance this stagnancy in perf per watt is you sort of have your traditional CPUs that to date have all fit on the right side of this. They're things like Intel Sapphire Rapids or AMD Genoa. These are what people think of when they think of a high-end data center server, kind of like the one I got in my closet over there, right? It's two-socket Intel, two-socket AMD machine. It's probably got about 10% down from the top of the SKU list in terms of frequency and core count, right? Maybe 15%, but that's what most people buy for their data centers. Because that's where the point of diminishing marginal returns is. And these chips have been built for a balance between high single thread performance, high memory bandwidth, and the ability for cores to communicate. What's happened is because CPU performance per watt has been stagnant, big hyperscale providers who are more concerned with selling dollars per core, dollars per thread type systems, they've gone to these sort of front end type CPUs like AMD Bergamo and Ampere 1. Which sacrifice the IPC of the core and the capability of the core. They have these really, really small cores, and they can fit more of them on the same silicon area. But they're not inherently more power efficient. You've just subdivided sort of the unit that you're using to do the work. A lot of people would rather have, for certain types of workloads, high single thread performance. If you, in a hypothetical scenario, had a chip that was twice as fast versus two chips that were half the speed. It would make it easier to distribute your work to have the opportunity to have that one high single thread performance chip. So this is a little bit troublesome for us because it means that basically energy efficiency gains are only happening in two of these three columns. We have energy efficiency gains happening in the accelerated space because of our GPUs growing 2x year over year, right, in performance. And we have energy efficiency gains going in these sort of front end workloads for people who want a core in the cloud and are going to have it mostly idle a lot of the time, but they want the maximum number of independent hardware cores per watt. But what we're missing is a power efficient solution that addresses what historically has been the highest volume market here in the last 30 years, which are these back-end CPUs that are used for high-end data processing and really feed your AI fleet. To this end, there's a lot of different processors out there, right? You have Ampere differentiating in smaller and smaller cores, but with that comes less capability per core. Curiously, one of the more successful ARM products to date has been AWS's Graviton. And even though they market it as an inexpensive way to get a core in the cloud, it's actually, from a design standpoint, very, very similar to some of these high-end CPUs. 64 cores, 300 gigabytes of memory bandwidth a second per socket. So Amazon understands that even to market something that looks like a $1 per core, $1 per thread type CPU, you have to have an efficient architecture to back it up that doesn't get bottlenecked on things. And then we have Grace, which is sort of a curious example because our design point is very much in this high memory bandwidth, moderate core count space. But we have incredible power efficiency. And what we've done is we've actually built a product that for general purpose CPU, this isn't going to be anything as impressive as the accelerator numbers you saw, right? You saw numbers on the accelerator side. There were 2x year over year performance gains. But Grace is doing pretty well from a general purpose CPU point of view. These are all open source general purpose CPU workloads. You install Linux, you type apt-get install, OpenFOAM or whatever. And you're able to achieve about 60 to 70% better perf per watt than some of the flagship parts from the best CPU providers out there at a loaded data center level. That's not the socket. I said earlier that NVIDIA, we're not a chip company, we're a data center company. So this performance per watt comparison includes all the stuff that I don't want to talk about that pulls our efficiency down. Things like fans, things like disks, things like NICs, things that drag my power efficiency down. We can still, with everything else in the box, hit about 60 to 70% better performance per watt. Put another way, you can fit 60 to 70% more servers in the same power limited rack with Grace, because in these examples at the center here, each server is doing about the same work. Basically, we're saying that Grace is as good as a flagship CPU, but you can fit 60 to 70% more of them per rack because of what we draw from a power efficiency standpoint at a loaded system level. So how do you design a chip, general purpose CPU that does these things? There's a bunch of different design points we used to try and achieve this. The first is that Grace is actually all about data movement. When we originally conceived Grace, it was designed to help our accelerators with a problem called Amdahl's law. Who here is familiar with Amdahl's law? You can do like a little show of hands on that. So Amdahl's law is sort of the idea. Imagine you're running an accounting company and you hire 10 accountants, but it takes you a certain amount of time to hand them the form and tell them, hey, this is what I need you to do on this form, right? And you have 10 accountants and you hand out the forms. Maybe handing out the forms takes you an hour, and each accountant can do a form in an hour, and then you spend another hour collecting them back out. So it turns out the GPU in this example is your herd of 10 accountants. If you go add 20 accountants, that hour that the accountants spend working on the forms goes in half. But the amount of time it takes you to distribute the work actually stays the same or gets even bigger. So even with your 20 accountants, you haven't really gotten the problem any quicker than 3 hours that you had with 10 accountants. Turns out the same thing is true of accelerated compute. You need a CPU that's very, very good at handing out all that work and giving the context behind all that work and collecting it. So when we originally conceived of Grace, we didn't focus actually on the core, which is the speed of the actual arithmetic, as much as we focused on the I/O and data movement. And we did this to help our accelerated CPU, to make it so that there are more cases where it would make sense for a customer to actually accelerate a workload. I know that's counterintuitive. Building a CPU differently changes what a customer can do in terms of accelerating on a GPU, but it's actually very true. That's kind of the heart of Amdahl's law. But it turns out that all these properties around data movement actually make a very efficient CPU, because when you make sure that every work unit on the CPU has access to the element that it's working on very quickly, you actually get more efficiency out of your core. It's no use having a Ferrari if it's not going anywhere. And so that's the kind of architecture that Grace has built that allows each core to be fed, happy, working all the time, instead of sitting there taking power, right, and sitting idle. That's very important from a data center performance point of view. So we built a CPU around good communications through the core. That's via our NVIDIA scalable coherency fabric. We built it on high single thread performance. We built it on high memory bandwidth. And all these things working together allow Grace to be a more power efficient CPU than a CPU that's just focused on how fast it can do the arithmetic. That's my sort of very high level view of how you design for power efficiency. There's also some other things here, like the fact that all of our cores are on a single piece of silicon. Costs us maybe a little bit more to build, but in a modern data center, the cost of that CPU silicon is tiny compared to what it costs to operate a machine. So why wouldn't you pay just a little bit more for your silicon and have that CPU go a much, much longer distance in your data center? So few design points there. I'll pause for questions here. Any questions, any discussion around this? Anything you guys have perceived in the market?
Eric, would you mind? I'm a slow reader. Could you kind of just share your question, especially the last one that you came up with?
Sure. So thanks, Ian.
Introduce yourself, right?
My question again is kind of a data center neophyte here. Is it safe to say that over time, and maybe that curve is essentially backwardated in some respects, if you will, that ultimately we're going to see GPUs cannibalize CPUs?
Yeah, I don't like using strong language without my PR team here, but I think that's absolutely the case. At the same time, one of the things that we've tried to do is build a CPU that makes it easier to accelerate portions of traditional CPU workloads. And actually, that's kind of where we were going with this next. We have this thing called Grace Hopper superchip as well, right? And remember, I brought up the sort of tax return problem and what that does with for both CPU and GPU parallelizing work. Well, it's actually a big issue on GPU workloads. So let me address that in one more slide. So we also have this product, Eric, that has the Grace CPU. And I talked all about all that data movement stuff we do. And we combine it with super high capacity, low power memory on the CPU side. We can achieve the same throughput between our memory and our CPU that a high-end data center server like from AMD or Intel does, but we can spend only 16 watts or so on memory, where they spend 60 or 70. We do this by using LPDDR. So all of a sudden you can have really, really fast memory, really close to your CPU, very high bandwidth to it. And then we take a GPU and we have super high bandwidth between the CPU and GPU. We've got about 6 to 8x the bandwidth of PCI Express going into this GPU. PCI Express is how all your GPUs were attached before to the CPU. Even in our high-end HGX 8-way systems, you still had PCI Express 60 gigabytes a second or so between the CPU and the GPU. And that was your communication overhead in that tax accountant problem, right? So now imagine that instead you can move the data at 450 gigabytes a second in each direction. You're able to hand out those sheets much faster. You're able to communicate much faster. And then the GPU has its own local memory. But we also have a trick up our sleeve. Imagine if instead of having to hand out the work at all, everyone in that room, in the strained accountant analogy, was already on the same page. They already knew what the other person was thinking of. That's what we've done with Grace Hopper. So we put a CPU and a GPU together on a single memory address space. So the CPU can reach into the GPU's memory and context, and vice versa. This is a really, really powerful technique that will allow CPU workloads to move to GPU. And the reason for this is before, if you wanted to have a CPU and GPU work together, right? Most of your workloads today, Eric, are on CPUs. So your kind of question about taking the CPU's lunch, right? Like most of your workloads by lines of code, not by volume. We have tremendous, by flops, it's probably still GPU today because of generative AI. But by lines of legacy code, it's CPUs. And the problem is getting that legacy code onto the GPU. And today, the way it would work is your code would have to stop, take a set of results, lock it, meaning the CPU isn't working on those results anymore, and has to copy it over that 60 gigabyte a second link onto the GPU. Then the GPU has to unlock the data structure, run, do its thing, and then the second the CPU wants to look at it, it has to lock it again and copy it back over that link. So that's really a lot of communication penalty. And what our new architectures built on Grace allow you to do is the CPU and GPU can literally just reach across that 450 gigabyte a second link, right? And they can do that already at about 7 to 8x the speed, but they don't have to lock the data structure. They don't have to stop their work. They can work in tandem on little bits and pieces of it. And what that means is there's plenty of workloads out there. This is an example called Abinit. This is a molecular dynamics package. And this bar represents the amount of time the CPU spends running on the problem. So this was a piece of CPU code. This was a CPU application. And about half of the code was really easy to move to the GPU. It was like replacing, it was a matrix solve operation. So it was like replacing a library call with a different library call, you know, a few hours of work maybe to move this to the GPU. And what happens is on a legacy type architecture, pre-Grace Hopper type architecture, which are great for doing work where the GPU is just running at full tilt all the time, you don't see stuff like this. But for this type of problem where you just wanted to take a piece of it that was running on the CPU, move it to the GPU, you got almost I think about a 10x speed up on that piece of work. See that teal bar? It's like 1/10 the size here. But the overhead of delegating the work from the CPU to the GPU introduced this new dark green bar. And overall, you didn't actually get that much faster. You got about 16% faster, which wasn't enough for anyone to want to go buy a GPU server or put this workload on a GPU. With Grace Hopper, that communication path goes down to a pretty negligible point. So all of a sudden, this workload, which was on CPU, was able to move to GPU and get a 4.25x performance gain just by taking a few library calls and farming them out to the GPU. And that's something historically that hasn't worked as nicely. So an answer to a very long answer to your question, but it touches on some of the content we wanted to cover, Eric. We see architectures like this unlocking the potential of acceleration for workloads that weren't accelerated before, whether they were, you know, just too hard to build piecewise like this, or they actually need the tight coherency.
So then going back to something you said on the front end, which is ultimately how can you get enough power into, let's call it the boxes, if you will, data centers. So is it safe then to say, regardless of time from an efficiency standpoint, but clearly we're going to have much denser from electricity demand racks. So maybe we can have smaller data center footprints, maybe not. Right. I think that's probably debatable, but it ultimately, the power consumption, the question is that power consumption, because what I've uncovered is these data centers are not terribly efficient, right? They operate at 50 to 60% efficiency from a power standpoint. They tell a utility we're going to take down 150 megawatts, and they really only eat 75, 90 megawatts. And so then, but they always need to have that power capability at any point in time. But it seems like overall the efficiency gains here, you're going to be able to move between applications much faster. Is that safe to say?
You're going to be able to take applications that weren't yet accelerated and move them to acceleration. And in doing that, the really, when you're operating a data center, the only thing you should care about, right, is the amount of energy or money or money, including energy, that goes into the coin receptor on the data center, and the amount of work units that come out. So even though a Grace Hopper node here might draw, I don't know, 1,000 watts, and the Grace node might draw 500 watts at workload power, so this requires twice as much power, right? You're getting 4x the work out of it. So I think that this might not perfectly address your question, and let me know one way or another if it does. But I think the kind of point of what we're bringing up here is infrastructure teams, people like yourself, right, and the people building the solutions, also people like yourself, people responsible for deploying actual applications, need to work together to pick capacity that optimizes that function, the coins in to work units out. And without having tight collaboration between the people building the infrastructure and the people building the work units, you're going to leave opportunities like this on the table, because you might look at something and go, well, that's 1,000 watts and that's 500, and not look at the fact that you're actually 2x perf per watt efficient in this example.
Got it.
Did that address your question?
That's really that's really the power of acceleration overall. Is you're right, your sort of power density is higher, but the amount of work you can do in that, because you're able to parallelize so much of the stuff for things that lend itself to acceleration, you can get orders of magnitude faster perf for that higher power density. So, that's kind of a big driver in how do you sort of, like Ian was saying, get more work out per unit of power that you put in, and that's just from the pure acceleration piece. And then, like we've been talking about, from, if you combine the efficient CPU and GPU and have the high bandwidth connection, you can now open up new things that were, didn't lend itself as well to acceleration. And it's, really just all about, optimizing your output, per square foot of data center, per unit of power that you send in.
I want to point out one thing. In the beginning, when we looked at CPU, right, I think we're all aligned that CPUs are only getting on this metric, raw perf per watt at a data center level. Because the CPU improves a little bit, but it's stuck in the rest of the machine that also draws power. You're improving on ultimate CPU performance per watt, not cores per watt, but the actual work that those cores do in aggregate. That's moving at about 5 to 10% every year. And with one move like this, even though you're replacing a 500 watt node with a 1,000 watt node, you're getting 200% perf per watt gain. So the other way NVIDIA thinks about this, right? This is a classic NVIDIA slide. This is one of Ivan's. It's quite good. You can spend $100 million on, and this is a more extreme example because this is more GPU-centric workload of today, but we're banking with Grace Hopper there will be more GPU-centric workloads enabled of tomorrow. But this is a AI inference example. You could spend $100 million on CPU servers, and it would look something like this. Actually, is this the one that I did the Excel for? The little rack map?
Yep.
and you can get 8,800 x86 servers, right? And they draw about 5 megawatts. And the amount of work units they push are 1.0x. You could spend $100 million on Grace Hopper servers, same amount of money, and you get fewer servers, so you're taking up less space. Eric, you brought this up, right? And you're drawing 3 megawatts, right? So there's another way to think about it for the same expenditure. So you save 2 megawatts, and you're also doing 12x the performance for this type of workload, for this AI workload. So all of a sudden, your power efficiency is actually the product of this 3 megawatts and 12x performance, right? It's not just one or the other, just as it is here. Another way to look at it is if you wanted to actually make the same amount of compute throughput as this. Maybe you only need 1x this throughput. Maybe all your users, maybe the token rate that's going on in your environment, maybe it just needs this amount of compute capacity. So for the same amount of compute capacity, you use 210 servers. You spend under a tenth the cost. You spend $8 million. And you spend about a 20th. Can I even do math today? Yeah, 20th of the power.
Hey, Ian, let's do another floor check in the group discussion here. I don't know, Marcin, Nimi, Pam, Terry, anybody else have questions from what you've heard? And you can see in the chat that working up to this, Ian has some questions that he put out there in terms of, well, how are your C-suite IT infrastructure and software workload teams actually addressing these limitations of data center and compute? Another one was, how does your firm plan to buy access to IT data center infrastructure? How is that changing? And what KPIs are you using? We've thrown around quite a few, but the floor is open. And so, Alexander, if you have something you want to add, Terry, Nimi, Pam.
Hi. Yeah. Hi, this is
Hey.
Pamela.
Good to see
Hi. Sorry, not on screen. Just finishing lunch. So actually, Leon and myself, actually, Alex, Enrique are work together here at Whirlpool. But I guess my question, I guess first to respond to your question, there's not a lot of thought right now in that space. We're mostly already moved a lot of our workloads to the cloud. However, Not all workloads are moved to the cloud, and of course, not all workloads are the same. I am thinking about our ERP, so SAP environment, our enterprise capabilities, and what this might equate to, say, in a location, a plant, that kind of thing. But I'm also thinking about how this, would be applicable to our virtual environments where we may want to um, push a workload. Say, I'm just picking a cloud, so don't take anything out of this, like AWS or something. And we want to configure that VPC with this kind of GPU capability for testing and for, exposing, some of this value and capability. So how would that be part of Graviton, or what, that kind of thing? Is that something already in place?
Right.
Okay, just wanted to understand that.
Graviton isn't our product. It's an example of another product. We at NVIDIA, we try not to cut down the competition. We try and recognize.
Understood.
Their,
Well, you can describe. I mean, pick GCP. That's fine. Yeah.
Yeah. So
Because I mean,
Graviton
I was at Next, so I did hear a lot about this, but this is real specific and very helpful. So I appreciate it. Thank you.
I'm glad to hear that, Pamela. Yeah, Graviton was an example of a CPU that we thought was doing things right. At the end of the day, when the CPUs go into a public cloud, right, what they do is they sell you a set of sizes, right? And those sizes are generally not a tailored suit. They're sort of the CSP has generally done the math that we're talking about here in terms of looking at a set of workloads and calculating the power encumbered TCO perf per dollar of those workloads. And they've tried to sort of fit the middle of the curve and offer a set of sizes that address each point on that curve that they think they can derive revenue from. They've tried to price them in such a way that, hopefully if your workload is at 10x instead of 15x, the TCO still makes sense for you. So at the end of the day, all the clouds are actually doing this on one side of the equation. And Pamela, what you as the customer can do is you can work across all the clouds. Probably you have one of choice, but you should also investigate, the full market of clouds that are out there.
Oh yeah, we are a multi-cloud environment, just to be clear. So
Excellent.
I just picked AWS as just an example. That's all it was.
No, that's exactly what you want, because what you can do is you can do, all of the economics behind this and all of the macroeconomic and laws of physics type drivers behind this scenario are happening in those clouds before they write out what they're going to charge you for each instance. It's the most valuable thing that I think groups like yours can do is work directly with the stakeholders who are consuming the work product and who are sort of setting, the amount of compute that's required, setting the deployments that are required, and actually evaluate, not take the cloud provider's word necessarily that one size is the same as another size, and actually do some real world workload evaluations on those clouds, not just to figure out which cloud offers a more compelling TCO, but literally which VM size or SKU or
Exactly.
or product.
Mhm.
Yeah.
Yeah, and just one last thing. I'm sorry, guys. With regards, we're planning to have an innovation summit here, maybe mid-November, early December. And one of my features and one of my areas of interest would be this GPU and capability for appliances. So if someone could reach out to me, that would be great.
Got you covered.
Excellent.
Hemendra, Marchin, Nimi, anything that you're seeing in the marketplace, questions that you have here? Terry, any questions that you might have from what you've heard? We've got Kevin.
Got a lively group today. Feel free to tell us if something here didn't land with you or didn't resonate. Is there anything in here that you think is just marketing fluff?
Yeah, here's one from Kevin Mullen. He said, do you anticipate large data centers more commonly engaged in corporate power purchase agreements? potentially even behind meter to improve access to power and overcome limitations? Or will it remain more of a traditional with public grid source power?
Well, people definitely optimize the locality of their data centers based on power. And there's certainly many types of compute heavy workloads that don't have a huge network latency requirement. So a lot of large HPE type, or sorry, large HPC type systems, Freudian slip there with our partner. A lot of large HPC type systems these days, if you look at a cloud provider that's building capacity for compute rich simulation, for instance, might be out in the middle of nowhere in an industrial area that used to have a high power requirement, and they've actually intentionally built the facility next to the power capacity. As to the terms of the agreements around those, I don't truly know. There's one of the problems with data centers is the loads are extremely unpredictable, so it makes it hard to do kind of the classic thing where you have the aluminum plant next to the power provider, and they call up the aluminum plant and say, switch all your loads from capacitive to inductive loads, or resistive loads. Like that's the kind of stuff that used to happen in these types of agreements. But running a hyperscale cloud requires much less predictability than those types of scenarios allow. So I'm not sure about that.
Got it. And Kevin, just to let you know, Jason replied, you probably saw it, so you guys can connect. Everybody gets each other's contact information. Any last word or takeaways that you'd like to share, Ian, before we close it out?
I hope that you guys learned a little bit about kind of how we perceive CPU and SoC design. I know that we kind of go from a top level down into a lot of detail, but I hope it was interesting. Hope you guys are also as excited as we are about the potential to go and get 4, 5, 10, or even 2x gains in performance efficiency, in the era where 10% a year is commonplace. I think the thing that you need to look at here is that GPUs can be a little bit intimidating at first. You have to program them differently. You have to move pieces of your workload. You have to get in touch with those pesky software developers and researchers and work with them to unlock those gains. But one of the really cool things that we've done in bringing a general purpose CPU to market is we've made it really easy to rip that Band-Aid off, because you can deploy just a set of CPU capacity. You can get 60% better power performance efficiency with the same workload, same code, just turnkey. Replace 3 racks with 2. And then you can start to work on that GPU Band-Aid. So it doesn't have to be scary, it doesn't have to be intimidating. And we're available to help in any way we can facilitate meaningful conversations between the groups building your software infrastructure and the groups deploying the stuff that it actually runs on.
Thanks, Ian. That's the last word for today. So folks, how was the expert talk and discussion? You can see that the survey's up. Please take time to fill it out and let us know. Today's post-show notes will hit your mailbox very soon with the slide deck, expert resource links, and all of your contact information so you can follow up, connect with each other. Next up on From the Experts, Solving Problems with AI continues with a new episode October 24th, where HP and NVIDIA share selected customer AI use cases, lessons learned, and they answer questions that might help you solve your problems faster. With over 2,300 members, 20,000 followers across 25 industries, the FT network is growing strong thanks to you and our sponsors. Please check out our library of expert content and never miss a show by subscribing to YouTube, Apple, and Spotify channels. And be sure to register for our next show like this one on our website at ft.network. Folks, we're out of time. Thank you once again, Ian, and all of you from the experts on the FTE show. We'll see you next time.